we can bring microbes back to life, if you will, that have been frozen in permafrost for 30,000 years. They're pretty badass. Like they'll put up with a lot.
Yeah, they'll put up with a lot. I get it. I should marry a microbe. Is that what you're telling me?
You already got a whole bunch more microbial cells in you than you cells, buddy.
Dr. Peter Girguis, welcome to Particles of Thought.
Thank you. It's a pleasure.
Yeah. So you're a deep ocean explorer, but you're not just thinking about the ocean. You're thinking about life in the ocean, microbial, and some macroscopic animals, and you're thinking about life off of the earth, right? Is that
absolutely
accurate?
Right. And I would suggest that if we really want to start thinking about life, say in our solar system, we got to start by understanding life on Earth, especially the microbes. Oh, and I can't help but toss out a fun fact, and that is microbes really rule this planet. I mean, they run the planet, and there are about 10 to the 27th microbes on Earth.
Wow.
And one of my favorite things to tell students, and this is legit true, is if you took those microbes, each about a micron in size, and you strung them end on end like pearls on a necklace, they stretch 105,000 light years.
What?
Right.
Holy cow.
Right. So, right?
Go ahead.
That's across our Milky Way.
Yeah.
That crosses the galaxy, right? So when I think of big numbers, I don't think of astronomical numbers anymore. I think of microbial numbers. And it's a reminder that there's a lot of them here. And with that being said, they work together to run the planet. And so if we want to think about life on, say, Mars or Europa or Titan or Enceladus, you look to Earth first and say, what are the fundamentals here? What is it that these microbes do and how do they make a living? And that helps us think about what to look for on those other planetary bodies.
Man, you know, as a scientist, when, you know, I'm skeptical. And when you first said microbes run the world, I immediately thought, not according to Beyonce. She's like, girls.
Well, okay, so in addition to Beyonce, microbes run the world.
All right. When I think of life, I divide life into two classes. Multicellular and not multicellular, right? Things like bacteria, archaea. And for me, that's a nice filter because I think about a random sample. If I were an alien and I came to Earth, for 8 nights of its history, there would not have been multicellular macroscopic animals. It would all have been microbes. So in a way, Earth is a microbial world.
Yeah. Now, you're warming my heart here, my man. So look, so we're human, and we've got these fingers and hands and brains and all this, and we breathe air and we live on land. So it's understandable that we have this bias to thinking of us as being like this pinnacle of life on Earth. And I don't want to cheese people off who believe that. Let me just say that this is very much a microbial world. And I'm going to give you some quick examples. When you think about the oxygen in our atmosphere, a whole lot of that was produced by microbes billions of years ago. The oxygen in Earth's atmosphere came from microbes. That's the deal. And so without that event having happened, you wouldn't have animal life as we know it today.
This is true. I know the plot where first oxygen takes off into the atmosphere, then you get the Cambrian explosion.
That's exactly right. We nickname it the Great Oxidation Event. It's just a fancy way of saying this thing happened where a bunch of oxygen showed up. And that's because microbes, for the first time, figured out how to, and I'm going to nerd out a bit, how to split water. Let me explain what I mean by that. A lot of us, at some point, have maybe read about like you can take a battery and you can take 2 wires and stick it in the water and you get hydrogen gas and oxygen gas, right? It's electrolysis. So in a very real way, a lot of the early microbes figured out, hey, I'm going to be a little anthropomorphic here and talk like they're talking to each other. But these microbes are like, I can take energy from the sun and I can split water and I can make a living doing that. I can make all the stuff I need to stay alive and give off oxygen.
So does it use the energy from the sun to split the water?
Absolutely.
Oh.
Yeah, super cool. And there were microbes before that knew how to use the energy from the sun, but not split water. And then this capacity is super cool. I don't want to drag us into the details, but it was a neat way in which these microbes, that we call them cyanobacteria, evolved this ability to use water and split it, and that gave off oxygen. And it was so successful because it yields a bunch of energy. They did great. They started flourishing. And guess what built up in our atmosphere? The oxygen.
Wait a minute. Is the oxygen their poop?
That's their poop. Look, one creature's poop another creature's breath, right? Like that's what. So actually, that creeps me out now. I think about it that way. Like we're kind of breathing, right? We're breathing a bunch of cyanobacterial poop, but it's true.
But that oxygen molecule started in the core of a star, then.
Which is even cooler.
It went in the water, then it became cyanobacteria poop.
Yeah, exactly. And so here, this little microorganism starts doing this, and they, by the way, they start, their activity leaves behind these really clear fossils. They're like, think of it as like chalk. It's a carbonate. So it's this big mound that we can see in the fossil record, and we can see little laminations where they grew and they grew. So. The reason we know they exist is because they kind of made their own sorts of rocks, these carbonates. And so we can look at them and like, that's where microbes were. All right, so they start putting oxygen in the atmosphere. This sets the stage for the multicellular life you were talking about for animals. Right?
Yeah.
Animals are cool because they build all sorts of neat body parts that are specialized. You know, so if you think about you and me, we've decided that a bunch of our cells are going to form our brain, and they're going to do the kind of command and control, right?
Well, because the point you bring up is something I talk about all the time, is that we are, and I wonder, because every cell is a living thing, and there are single cells that live out there as single cells, but we're made up of a bunch of single cells.
Right.
So are we us, or are we a colony of gazillions of individuals?
Yeah, that's a great question. Let's start with the us cells.
Yeah.
We're us in that we have sort of decided, and forgive me for being again a bit kind of anthropomorphic here, but our bodies are like, we're going to have some cells do this job of command and control, and that frees up the muscle cells in our bodies to be muscles. They don't have to worry about command and control, right? So this tissue specialization means we've got organs, and that lets us do crazy cool things like walk around, eat a cheeseburger, pick a fight, run for your life, whatever it is.
Right.
So that's what animals are good at. There are some trade-offs though, and I'm going to tie this into oxygen.
Yeah.
We animals, and basically every animal on the planet, can't live without oxygen, because the only way that our bodies can harness energy is by eating dead stuff or live stuff, if that's your thing. You eat stuff and you basically burn it with oxygen. You oxidize it, right? That's what we do. And that's what all animals have to do. That's the only way we generate enough energy, harness enough energy to stay alive, right? Because it's not created or destroyed. We are just harnessing energy from these reactions. Okay, so far so good. That's what animals do. But the trade-off is that's the only thing they can do. There is no animal alive on Earth that can live off of rocks. But see, microbes can. That's what's so cool about microbes, is that there's so many different kinds of microbes. They can make a living off just about any pair of chemicals that can react by passing electrons to one another.
Wow. And that's a lot.
That's a lot. So there's like microbes that live off of uranium.
What?
Yeah. And this is even cooler. They've evolved the ability to deal with radiation damage to their DNA, because they have like 12 copies of their genome, and they just fix the errors every time. Yeah. So microbes can do all this stuff, and they can eat all sorts of different foods. We animals, we're stuck with breathing oxygen and eating organic matter. Scientists call this aerobic respiration. So animals are great, they're successful, but it's like this deal we made with the devil a long time ago. Like, okay, I'll take one of the best ways of harnessing energy. I'll take that and I'll do all this cool stuff, but that's all I can do.
Wow. Yeah.
And for a long time, this was just a microbial world.
This podcast is from the producers of Nova. Nova is supported by Carlisle Companies, a manufacturer of innovative building envelope systems. With buildings responsible for over a third of total energy use, Carlisle's energy-efficient solutions are built to reduce strain on the energy grid. For example, Carlisle's UltraTouch denim insulation, made from sustainable recycled cotton fibers, delivers energy efficiency while being safe to handle and easy to install. Made with 80% recycled denim, UltraTouch diverts nearly 20 million pounds of textile waste from landfills each year. Operating across North America, Carlisle is working towards a more sustainable future. Learn more at carlisle.com. Are there any animals, this is weird, that have both gills and lungs? I would love that, right? So I could dive into the ocean.
Yeah.
Because I just discovered that the southern elephant seal can stay submerged for 2 hours.
Yeah. Yeah, it's pretty badass.
Yeah, without gills. Yeah.
It's pretty badass.
Yeah.
Yeah, so are there animals that have both? There are some definite funky animals out there. And this is one of the things I love about animal physiology and biochemistry, which I started off with in graduate school, is that animals have evolved all these cool tools to do different things. Like, let me give you an example. There are some frogs that have patches of their skin that's transparent, and they can suck up oxygen just through that little skin.
Through the water or the air?
Through the water, right? Or the air, actually.
Or the air.
The punchline with getting oxygen, right? For all animals need oxygen. The punchline is you need to be able to get as much oxygen as you need, but that surface also gives up water. So our evolutionary kind of compromise are lungs. So we can breathe in oxygen and exhale it, but it really doesn't work as well as some other kinds of gas exchange things. So animals are cool because there's so many different designs to solve problems.
Yeah.
But like, none of them are perfect. They're all a compromise, right?
Yeah.
And that's okay. That's cool. It works.
Right.
But there are some creatures out there that have a little bit of both, and they live in crazy, weird places, like African lungfish, right? Which do really well. So, yeah.
When you talk about this being a microbial world, two things come to mind. One of them is mass extinctions.
Yeah.
And right now we're suffering this loss of biodiversity on Earth, right, due to, people think human activity. But microbes aren't suffering that. And then, there's the big extinction that occurred, and that was the only mass extinction allegedly that insects suffered, I've heard somewhere.
Right.
Is there a known record of microbial extinction events? Like global
great question.
Scale?
That is a great question.
Yeah.
I don't know.
Yeah, I've never heard that.
I kind of doubt it.
Yeah.
But I want to let's take a step back and say that mass extinctions have been a part of life on Earth since there's been life on Earth, and there's been many. And if you think about it, if we make an estimate, probably about 98 or 99% of all of the biodiversity that's ever existed on this planet is gone.
Oh, wow.
So the diversity we have today is precious and important.
Yeah.
But I do think we have to sometimes remind ourselves that things evolved and go extinct throughout Earth's past before humans ever tinkered with anything. Right? Now, microbes are wild because it's really hard to know what a microbial species is.
So when you see different bacteria, I mean, they're shaped differently.
They're shaped differently. So yeah, we got some different shapes. But let me put it this way. Despite your best efforts, if you fall in love with a cat, you're not going to have a cat-human baby. Right? That's like not going to happen. It's not in the cards. But microbes are kind of, how do I put this? They're sort of floozies with their genomes. What I mean is they can swap genes all the time.
With other
all the time.
species?
Oh, absolutely, all the time. Yeah. So if we rely on a genome to say, okay, this is Hakeem, and Hakeem's a human because this is what his genome is, we lose that in microbes. Like we can't do that very easily. So have microbes suffered mass extinctions? I'm willing to bet there are certain microbes that were alive on Earth in the past that aren't alive today.
Yeah.
Because the conditions on Earth don't favor them. But I don't know if I could call that a mass extinction in the way that, if we have a meteorite or an asteroid impacted and we have this die-off of animals. I don't know that they're the same.
Right.
It's a great question.
It's a different, that's a very different realm of existence.
Yeah,
the microbial realm, if you're doing that.
Yeah.
So let's get back to the ocean.
Sure.
So
my favorite place.
I heard you said something about the ocean ecosystem and how it differs from our land ecosystems that we have contact with every day and think about. Go into that for me.
Yeah, sure. So so let me start with a bit about the ocean, right? It covers the majority of our planet's surface, and it is a huge part of what makes our planet habitable and comfortable for us. And I want to make it clear that you don't need an ocean for a planet to be habitable per se. You need water, but I want to make it clear that that the world as we know it today is really useful for us and for other animals, right? The ocean tempers heat, like it absorbs heat and releases heat. It keeps our planet from having the wild temperature swings that you know better than I do happen on on the moon or on Mars. There's like crazy temperature swings. All right, but the other thing is the ocean is so foreign to us that sometimes it's easy to lose sight of just kind of how different a place it is. So check this out. So sunlight goes through the ocean, right? And it disappears at about 1,000 meters. Okay. And we call that upper 1,000 meters the epipelagic and mesopelagic. These are fancy names we come up with. But below that, we call that the deep sea proper, or bathypelagic.
Okay.
Now, the deep sea proper is the ocean beyond the reach of sunlight. And when you think about its size and its volume, you realize that 80% of our planet's living space is deep ocean.
Oh, wow.
Right?
Yeah.
Super cool,
yeah,
right?
Super cool. 80%.
So 80%. Now, so that means everything else that we think of off the top of our heads, the Serengeti, right? The Amazon rainforest, even the shallow water coral reefs, Washington, D.C., Boston, Paris, you name it, all that's in the other 20%.
Wow.
And I've said this little fact.
Because you have that top layer of the ocean, I would imagine that a big percentage of the 20% is that sunlit part of the ocean.
Yeah, that's right.
And the land,
that's
because because the vertical extension of land is to the top of the tree canopy.
Yeah, that's right. That's right.
From the ground
that's right. That's it. And so
and
even that other 20%, a bunch of it is ocean, right?
Right.
So you know, if you're talking about aliens, right? So I love saying that if aliens came to Earth and they had to go back and tell their leader what the typical condition on Earth was like, they would tell her it's cold, wet, dark, and salty.
Cold, wet, dark, and what else fits that description?
Yeah, right.
Cold, wet, dark.
I'll let you run with that one.
I can't think of anything. Right? I can't think of anything.
So because it's cold, ice cold seawater.
Yeah.
Right.
Yeah.
Now, that is really interesting, right? Because it means that this part of the ocean, and we're just barely like getting eyes down there, right? Like we're just barely starting to study it and understand it. That's our planet's sort of largest living space. Now, in fairness, just so I don't want to paint an inaccurate picture, most of the biomass, like most of the stuff that's alive on Earth, lives in that 20%, because the sun is our planet's power source.
You know what? This is my insight that I have been telling my colleagues for the last decade or so, and my students. I was like, what makes Earth special is not the fact that it has an ocean. It's the fact that our ocean is bathed in sunlight.
Yeah, totally.
Yeah,
totally. And thank you for doing that work, Hakeem, and telling people, because in my even in my ocean world, many scientists are like, oh, well, water is unique to Earth, and we know it's not, right? There's quasars that have 1,000,000 times more water than Earth does. But it's that bathed in sunlight, and that lets these photosynthetic organisms like algae and microbes and plants, they do the work of harnessing energy from the sun and turning it into biomass, and everything else lives off that. So what's cool is our planet, our biosphere, our lives, we're fueled by a star.
Right. Yeah.
What I think is also cool, and what fascinates me about the deep sea, is that there are microbes that live at underwater volcanoes, and they harness their energy from volcanic gases and chemicals. So they're actually fueled by the planet's core.
Wow.
Which is cool.
Yeah.
Because it's different. Yeah. And that is why myself and others, many of my colleagues who study these ecosystems, why NASA turned to us and they're like, hey, y'all think about these microbes that live off of planetary chemicals, right?
Yeah.
Can you help us think about what life might look like? What would it take to keep things alive?
The ice of Enceladus or Europa or the thick atmosphere of Titan, perhaps.
Right. I'm not Hakeem. I'm not an astrophysicist. I have nothing to contribute there in any deep, meaningful way. But when we understand how these organisms on Earth can make a living off volcanic gases, let me give you an example of an interesting organism. These microbes called methanogens. They make methane.
Wait a minute. Aren't those the same ones? I hate to go back to this topic again, but aren't those the same ones that make farts in our gut?
Yeah, you carry around your own little methanogen colony, right? And those microbes, a lot of them make a living by taking hydrogen gas and carbon dioxide, and they react them, and they poop methane. That's what they do, right? And when we go to places like Enceladus, and you got things like Cassini catching little whiffs of water vapor or CO2 and hydrogen, because there's a little plume. first off, the plumes are like, well, how'd that happen? Where's that coming from? That's above my pay grade.
Yeah.
But my astrophysics colleagues and geophysics colleagues are like, yeah, that suggests there's some kind of hydrothermal activity maybe. But it's the chemicals in there that catch my attention. Because if there's hydrogen and CO2, that checks this first box of, are there the chemicals you need to keep something alive? That's just the first box, though.
Right. Yeah.
And so, it's looking pretty promising in that regard. And now we have the hard work of saying, okay, what else might be needed to actually sustain a microbial community, to have them live and evolve, right? And that's a tougher question.
So is this, surface life photosynthesis?
Yep.
Is what you're describing what I've heard the phrase chemosynthesis?
That's it. Yeah.
Are there chemosynthesis processes that result in the production of oxygen, just like with photosynthesis? Since photosynthesis comes in two types, does chemosynthesis also come in two types?
That's a good question.
Yeah.
And I think that there's been a bit of work in thinking about, can you have chemosynthetic oxygen production? Let me actually tell you, this brings up a little sidebar comment I want to make. Recently, there were scientists studying oxygen on the seafloor, and they were measuring oxygen in this area where industry wants to do deep sea mining. And it was just part of, let's figure out the microbes, the animals, and all that jazz. And what they noticed is that oxygen was being produced on this part of the seafloor, beyond the reach of the sun. There can't be photosynthetic oxygen production, but they're calling it dark oxygen production.
Interesting.
Right. Super cool. And this has turned into a kind of a hot topic because people are like, wow, are microbes producing oxygen from chemosynthesis or some kind of chemical reaction? I think the answer is trying to be a good scientist. I'm like, sure, it's plausible. Let's talk about that. But I also think it's possible that these just abiotic, non-living chemical reactions.
Processes.
Yeah. Like we'll call them electrochemical reactions, where you have two different minerals.
Yes.
There might be oxygen production from that. Yes. So let's give the authors the benefit of the doubt and assume that oxygen is being produced there. Fine. Let's also pretend that could happen on something like Enceladus. That's fine. My job and the job of my colleagues who are thinking about this is to ask, is that enough to actually sustain a viable population? You see, it's one thing to be like, let's be Star Trekky here.
Right.
If I wanted to beam a bunch of methanogens to Enceladus, I'm like, beam them into the Enceladus ocean. Could they make a living? If there's enough stuff, maybe. But that's not what we're asking. We're asking is there enough energy available for those organisms to evolve and sustain and perpetuate and reproduce and all those things? That's a different question.
Different question.
That's hard to answer.
Yeah.
So that's where we're at.
Yeah. Is there any sort of theory on that allow you to model it? Like, let's plug in the values and see if it crosses the threshold of sustainability.
I'm going to give a shout out to a bunch of my colleagues that I've been working with over the last few years with support from NASA, who I think smartly said, you all should get together and use your different talents to think about this. So a fellow named Chris German at Woods Hole Oceanographic, who is known for discovering and finding hydrothermal vents, he brought a bunch of us together and said, let's put in this proposal and do what NASA wants. So myself, I have another microbiology colleague named Julie Huber, a fellow named Tori Holder who works for NASA Ames. There's a guy named John Marshall at MIT, who you may know does a lot of cool geophysics work. We're trying to build a model right now as a team.
I see.
As a team of asking, can we predict to some degree how much life could be supported in these areas, right?
Wow. So one of the most interesting ideas, well, not interesting, but divergent ideas I've heard about life is radioactive comets. If you have, so comets, the ices provide the water. You have some uranium or something in there that is a natural reactor.
Yeah.
It melts the water. If you have the right, your N-CHOPs, nitrogen, carbon, hydrogen, oxygen, phosphorus, sulfur, you could get life.
Yeah.
And the other thing I just saw recently was this study that showed that, you don't necessarily need a lipid cell wall. These droplets. Did you see that one? It's very recent paper. What do you think about all those very divergent ideas from what we normally consider?
So I'm going to give you two answers. One is we as scientists are trained to be cautious, and that's important. It's important. We should not give that up. But I think it's equally important that we be open and imaginative. And so right now when I read about those ideas, I was like, man, that's wacky. But in a way, who am I to say no to that? My job is to gather enough data to test and poke at those ideas. Right. Yeah. So right now, I would say the deck is stacked a little bit against them.
I see.
But I think it's really bad form as a scientist to just rule something out because you're like, I just don't believe it. That's nonsense. Our job is to test it.
Right.
And they're cool ideas.
Yeah, they are cool ideas.
So we know that living things can harness energy from light, photosynthesis. We know that they can harness energy from chemicals. But is it possible that they could directly harness energy from other forms of radiation? I don't know. I don't know. I'm not really ready to rule it out. We just got to be cautious and think about them.
Well, that's where astrophysics comes in, because you get the big numbers, right? Hundreds of billion stars in the galaxy, hundreds of billions of galaxies. Well, hundreds of, exactly. So you actually, though, go deep in the ocean yourself. Man, listen, people always ask me, if aliens came, would you go with them? If there was an opportunity to go to Mars, would you go? And I'm all like, hell yeah, yes, I will go, right? I don't want to go to the deep ocean. That's scary.
All right. So for fun, I'll tell you a little bit about what it's like to do that. So I dive in a submersible called Alvin, and it's been...
Wait, is that the famous one?
That's the famous one.
Yeah.
Right, and it's been doing work since the 1960s. Totally different. It's been rebuilt. It's not the same sub, but here we are. It's a 2 meter or about 6 foot titanium ball. That's the dimensions on. It's actually about 6'2" now, because I can stand up and touch my head. That's about my height. So you get in there with 2 other people. And you're
in there. You doesn't sound like you fit.
You're looking at me. You're saying I'm a big guy. Do I fit? Depends on
you and
the other
2
people
other
in there. From my point of view, I'm comfortable. But the thing is, you get in there with 2 other people, and it's cozy. And I got to tell you, I don't like confined spaces. But let me explain why this works. Because the moment they put the sub in the water, and you're looking out your window, and you see the ocean, once you get past that nasty, disgusting feeling on the surface, you're just down 5-10 meters, about 20-30 feet. It's magical. I forget that I'm in a little ball. I mean it. I completely mean it, because I'm looking out the window, and as you go down, you start to see bioluminescent organisms, these creatures that light up, and it's a light show. I mean, Hakeem, I am not exaggerating to say it's like these incredible moments that I just never forget. I've been on about, I think, 9 or 10 of these. They're amazing. So I don't like small spaces. This is really different, though.
This is really different. Wow. How deep have you gone?
About 4,000 meters, something like that.
4 kilometers? 2 miles deep?
Yeah.
What?
Yeah, isn't that wild? Yeah.
Wow, that is wild. So what happens with, is kept at just straight atmospheric pressure?
Yeah, it's a big old titanium ball.
And is it the same gas mixture that we're breathing right now?
It is. It's air, and I want to also say, it's cool that they designed it to be so simple and reliable, and knock on wood, right? This thing's been diving for a long time, and there are many submersibles. There's about 24 deep diving submersibles worldwide, and they do great.
What's the duration of the time of ascent, descent, and staying at depth?
It's about 8 hours total, right? So we get in the morning.
Wait a minute. Where's the bathroom? Never mind.
So here's the deal. You get in, and it's 2 hours to the bottom. And then when you're down there, you got about 4 hours on bottom, 2 hours back up. And if you have to pee, we're professionals. And so you hand a person a pee bottle, and the other person, she or he, stands up, pees, everyone looks away, and you move on.
Do you ever get scared down there? You ever hear it like creaking and cracking?
Only on my first dive. So here I was a graduate student. I've been a graduate student for 1 month. And I get in the sub, not with my mentor, but a guy whom I had turned down for grad school. He tried to recruit me.
Oh, that was a setup.
That was a total setup. So he's on the boat. I'm in there with him, and he's pretty cool. But he decided to navigate to our dive site using a Xerox copy of a map from National Geographic, even though the originals were on the research vessel. No, it's my map. Anyway, I don't want to badmouth him too much, but we end up in totally the wrong place, and we run out of battery power. So the pilot has to shut everything down, and I didn't know what the hell was going on. So I'm freaking out. And I'm like, I'm gonna die like on my first dive. This sucks, right? Well, it's a Navy-owned sub that we just turned down the power for science. There was a whole other battery pack, and we weren't in any real danger, but I didn't know better. But that was the one and only time where I turned to this guy. I'm like, I'm glad I didn't go grad school with you. You're like an idiot. You know, I was so mad.
Well, I was imagining, like, is there a hand crank for to recharge the battery, you know, with a generator down there?
Actually, that's genius. But no, there isn't. So, no, but that's it. I mean, honestly, it's otherworldly, you know? And like you'd go to Mars in a heartbeat because you know it would blow your mind.
Absolutely. You know, it reminded me, I went to one of my dream destinations, which was to fly on the zero-G plane.
Oh, you
I
did?
it exactly a year ago.
Oh, wow. So cool. The vomit comet.
Until it wasn't.
Oh, right. Okay.
I learned why it's called the vomit comet,
I got
man.
it. I'm with you.
I went through 30 cycles.
Wait, really? I thought they did like 2 or 3.
No, they do 5 in a set typically.
I see.
But I was on a special research with all these NASA experiments.
I see.
And I made it through the first 10, which for me is pretty
good.
Yeah, it's pretty good. But the next 20, man, it was pure misery.
That's I thought you were going to say we're going to try to break Hakeem. They're like, let's keep going until we bust
they
him.
achieved it.
Oh,
they didn't
my
have
gosh.
to keep going
That's
until they broke
brutal.
me. One of the ways that science made a difference in my life, you know, growing up from a humble circumstances, is, you know, I never thought I'd be able to travel the world, except for when I was young in the Navy, right? But I didn't do that. And now I've been in like over 40 countries, right? And it's all, every trip was free because it was a science trip, right?
Yeah.
I imagine that this, you know, I've been to Indonesia, and you know, that part of the world is so different from our east and west coast here. Then you have the Arctic Ocean, the Antarctic Ocean, which will kill you in this heartbeat. Where have you been, man? What are these? The Mediterranean? What oceans have you descended into?
Great question. I most of my work has been in the Pacific, along all the way from about the coast of Vancouver in California. In Canada, Vancouver in Canada, all the way down to the Gulf of California. That's where most of my work has been.
Yeah. Is it because of the Ring of Fire volcanism?
That's it, But I've been, I do work in the middle of the Atlantic, in the Gulf of Mexico, and this coming year,
When you say middle of the Atlantic, or are you talking about the Mid-Atlantic Ridge?
Yeah, that's exactly right.
Okay.
And we're trying to figure out, actually, the microbes that live deep in the subsurface off the Mid-Atlantic Ridge. So, and a lot of these cruises these days use a robot sub. And yes, safety matters.
Right.
Some people think it's more cost effective. To be honest, it's about on par with a human-occupied submersible. But a big reason to use a robot sub is that I can take the video from that robot sub and beam it to a satellite and send it to you. Hakeem.
Wait a minute. While it's in the water?
Yeah.
Because I was wondering earlier about when you mentioned that, how you do navigation, because I would assume there's no GPS.
No GPS. That's one of the sucky things about water. And makes it hard. And why we don't know as much about the deep sea as we really ought to is that we don't have GPS, we don't have Wi-Fi, we don't have Bluetooth. All of these wireless ways we communicate here on Earth, to fly drones, none of that works. None of it works. The way we communicate through water without a wire is to yell at each other. And I'm being cheeky, but literally we use these things called acoustic modems. That's the most common way to do it. And you basically send data as sound, and you have a microphone listening for it.
What?
Yeah, and the speed of that is like the old school dial-up modems.
You're being dolphins and whales, right?
Totally.
Yeah, but the speed is like...
but poorly. Right, so and now we got cool optical modems. There's new stuff coming out.
Is it a binary, just coded like
it's usually
digital
coded,
data?
Yeah, it's usually coded like that. Sometimes we actually use our voice, but the most of the time, we just don't have the means to communicate that swiftly and quickly. So we send a robot sub on a tether. Fiber optic tether.
Got it.
And the robot sub itself uses many kilowatts. Like, we're pumping a lot of power down to this robot
so
sub.
it's plugged in.
Oh, absolutely. Yeah, to a big research vessel. So once we have the signal on board ship, we can send it up to a satellite and send it back. Even before Starlink. Like, there's been satellites orbiting the Earth and doing live telecasts of, sports events and all that forever. So we send it up and then we send it back down. And now that means, Hakeem, I can involve scientists and students in classrooms around the world, right?
Wow.
And this was something largely pioneered by a guy named Bob Ballard, who discovered the Titanic. And to his credit, he had the foresight to say, this is a cool way to engage people.
Yeah. So you can do a live from the...
live from the seafloor. So in fact...
Live
if you want to watch it live, when we're working out and we're going out in November and February, you can go to YouTube and watch our research dives live.
And how do people know when they're going to occur so they know to tune in?
We try to post
your social media?
Yeah, we try to use social media, right? There's a few different organizations that do this now, but I think where I think we can still do better, Hakeem, to be candid, is right now you can tune in and you can watch, and it's not especially interactive, and scientists don't use this to its full potential. So a big part of my life now is saying, scientists, when someone goes to sea and they're studying a hydrothermal vent, let's invite another 10 or 20 scientists around the world, colleagues from Ghana or Brazil or Argentina or the Philippines. Have them chime in and ask for samples, and let's really support one another, because there's so much work to do.
So they can actually say,
absolutely,
oh, I see something there. You need to get that.
Yeah, that's my dream. And we can do it now. It's a little clumsy, but I'd love for us to, as a community, lean into this.
So what types of sample grab capabilities do you have? If you're studying microbes, I'm guessing a scoop of sand or chunk of water. I don't know what you call a small volume of water.
A parcel.
A parcel of water.
Yeah. How do we do that? It's a great question. The robot subs and the human-occupied vehicles have manipulator arms. They actually, speaking of being adopted, they came from the nuclear reactor industry. So they use these robot arms to do things inside in the presence of radiation, and they have now adopted them for these submersibles. And so they can do things like pick up this little cube. They can grab eggs without cracking them. Like, no joke, they're really good. And we have all the other tools we develop, like water samplers or little suction devices. So we've got...
What about, like, when you send something to Mars, it drills into the rock and takes a core sample?
We suck at that.
Oh,
we kind of. My colleagues are going to hate me, but like, we've tried to make these drills for a while, and the ocean, sort of oil and gas, they drill all the time. It's challenging for us because you've got this big thing in the water, but it's floating, and so you try to drill, you push against something, you're going to have an equal and opposite force. So we're getting better. But there's a long way to go before it's a normal tool, and that's. We got work to do in that regard.
And I guess you're limited in the size of what you can bring
100%.
back as well.
Yeah. Now there's a whole ocean drilling program with a ship that does deep cores, but that's a separate thing.
All right, so let's go back out to space a little bit.
Let's do it.
And let's go to the red planet, because we are recording this on September 10th.
Right.
And there has been an announcement from NASA, and let me read this. It's a quote. Just a few hours ago, NASA had a big press conference saying they've discovered what, I quote, very well could be the clearest sign of life that we've ever found on Mars. Let me catch my breath.
Take a deep one.
Bro, seriously? Like, clearest sign of, those are clearest sign of life. Like, I would be happy with a sign of life. There are pictures. Right? What NASA points out in this image is something called a leopard spot. They circle this rock and say leopard spot. So I'm guessing they're not saying that a leopard spot fell off a leopard on Mars and now it's right here on the ground, right? It's some sort of mineral signature. So what is going on with the leopard spot that seems to make it the clearest sign of life yet?
So understandably, NASA scientists, like the rest of us, we give these things nicknames. And so if you look at the photo, you can see that it's got these speckles, right? And it kind of looks like the spots on a leopard. And this it looks like a sediment deposit with different kinds of minerals sort of sprinkled in there, if you will. And what's really exciting is that those minerals have very different chemical properties. And so on Earth, you don't usually find them next to one another unless some microbe has been involved. And I want to underline the word usually.
Usually.
Right? So this, I would not read this as a smoking gun that there was a microbe. But what it does suggest is that, like here on Earth, when we see these different kinds of minerals side by side, that chances are there's some microbe that did this. And in the case of Mars, there was a microbe that did this in the past, and this became preserved in this sediment. That's what's exciting. That's why the NASA scientists who are publishing these data are like, this smacks a bit of what we see microbes doing on Earth.
Wow. So in this particular sample that NASA has produced, why is it that them being in proximity, I get it that they're in proximity, but why does life put them next to each other versus a non-living scenario?
One of the things that I've been alluding to is this idea of life out of disequilibrium and disequilibrium from the environment. So what I mean by that is we know, for example, that there are microbes on Earth that in the deep ocean sediments, when you get a few centimeters or a meter or so into the ocean sediments, oxygen's gone.
Okay.
So there's no oxygen, dioxygen, right? There's no oxygen gas dissolved in the water. In many of those places, there's iron oxides. Just call it rust, generically speaking. Different forms of it, right? But there are microbes that can take that rust and they can breathe it. The way you and I use oxygen gas, they will breathe that rust through a really cool process. And in so doing, they will produce non-rusty iron or iron 2. Right?
Yeah.
And that's often soluble, but sometimes it reacts with elements. And I have a buddy, Brandy Toner in Minnesota. She loves this stuff. She's good at it. And what she does is uses really cool probes at like the synchrotron facilities, these places where you can like zap things. And she looks for different mineral phases. And if you've got a rust sitting next to a non-rust, unless it's in a specific place like a vent, right? If you got that sitting in deep sea sediments, there's a good chance a microbe did that.
Oh, it's kind of like with uranium decaying into lead.
Yes.
You see this?
Yes. Right? Yeah. And so this particular combination smacks of some microbe breathing this oxide and turning it into making this iron 2.
Yeah.
That's why the lead scientists were excited. Because we see bits of this on Earth, right?
Right. So for these particular minerals that they found on Mars, where do we find the same mineral side by side on Earth?
Yeah, it's the same. It's underwater hot springs. It's deep sea sediments, right?
I see.
They're iron-containing minerals.
Yeah.
And they're it looks like a microbe could have been breathing one and producing the other.
So is it always deep sea? Because on Mars, Jezero Crater is sort of like my understanding, it has like a river delta type situation where water was flowing into a crater lake.
Great question. It's not always deep sea, but the reason on Earth it's often deep sea is because we have this atmosphere full of oxygen. And the moment a microbe on the surface takes, say, rust and turns it into this non-rusty iron 2, atmospheric oxygen messes with it.
Right.
So we've got these minerals. It's unusual to find them juxtaposed. And there they are, sitting side by side in this mud. So here's what I think is cool. Here's where I agree with NASA. This leans towards something less unusual. It's something unusual. Yeah. And so it means that these minerals, which are vivianite and greigite, if I remember correctly, the fact that they're near each other is similar to what we see here on Earth. So it's sort of circumstantial evidence.
Yeah.
But it's cool.
Yeah. Yeah,
it's a good place to look.
Yeah, it's a step in the direction of finding life.
Right, and as much as I'd love to tell you that we scientists come up with like silver bullet answers, like the bullseye on a target, that's not how we search for life.
So for example, we talk about early life on Earth. There are these zircon crystals where they look at carbon isotope ratios.
Yeah, totally.
So let's talk about signs of life.
Let's do it.
When I talk about what's different about Earth's life is that it's bathed in sunlight, what I'm getting at there without saying it is that most of the oceans are under miles of ice, miles of rock, or a super thick atmosphere, whereas we have this little tiny thin atmosphere, right?
Completely.
So if I wanted to look for signs of life, you can do it both remotely and you can do it, from a distance, right? And you can do it by sending a probe there, right? And aside from finding critters crawling around or skeletons, what are the different ways that you could potentially tease out that there is microbial life?
Yeah.
Because I'm guessing that is the standard. If life exists 9 times out of 10, just like on Earth, if you visit Earth throughout its history, most of the time you're only going to find microbes.
Yeah, right.
How do you go about, what are the different indicators that you could possibly that you guys have thought of so far?
So a bunch of scientists like myself, we study life on Earth through I'm going to call them different lenses. So some of my colleagues think a lot about DNA and genomics. And of course, if you find a molecule like DNA, and if you can be sure you didn't drag it to Mars with you, it's pretty cool. Right?
Yeah.
So that's because that's like information in a molecule.
So finding a molecule, a life molecule, that is unquestionably a life molecule.
Yeah, and let me give you a kind of little bit more there. Some of my colleagues are asking, like, how small does can a small molecule be before you're sure it's not life? Or another way of putting it is like if I find, let me take acetic acid, which is vinegar.
Yeah.
If I find vinegar molecules on Mars, that doesn't mean anything. Because you got all these like little organics floating around in space. But what if you find 10 things strung together? Can that happen without life? What if it's 20 or 100? So what I'm getting at here is there's something about the complexity that can give us a hint as to whether or not this was produced by a living thing. You know, your DNA is like millions of little bases strung together. That's cool. That's a lot of complexity. So if we found something that's 1 million bases long, like, come on, like that's pretty clear.
Yeah.
So that's one lens. People like myself, we think a lot about energetics, as you kind of gathered from me talking, right? One way I define life is like it's got to keep itself at disequilibrium from the environment. And if I had those Star Trek tricorders, I could walk around and poke at things and be like, oh, look, that's the right mix of different elements all wrapped up in a little bubble that it may have been at alive at some point.
Right.
But the challenge with that, what makes it hard, is if I kill you, and I don't mean to be creepy here, but like let me back up because this is a bad thing to do on your show.
in 2025.
Yeah, I know.
In 1975, perfectly fine.
Can we edit that out?
Yeah,
no. So if something dies and we bury it, it goes to equilibrium over time, and we can no longer tell it's there. Yeah, right? So you take it, if you take a piece of cheese and bury it in your backyard and over a century you go back, like you can't tell that a piece of cheese was there. Those chemicals diffuse, they get washed away, and all that stuff. You see where I'm going with this?
I see where you're going.
So when we go and look for life on Mars, and if it's, 2 billion years old, we're not going to find an intact cell with all those elements in there. So my disequilibrium model is tough.
Yeah.
So is looking for DNA. So the way we approach this is we take all of these 5 or 6 or 10 different ways and we try to overlap them. If I got a little bit of evidence that leans in the right direction and someone else has a little bit, you can imagine starting to say, okay, this is more consistent. We got 5, 6, 7, 10 lines.
It becomes more than a coincidence when you have all of these things.
That's it. Because right now we got 2 minerals.
Yeah.
That's where we're at.
2 minerals.
It's a good sign.
that's not your millions of things strung together. Oh my goodness.
Right.
So what would conclusive life look like then at the microbial level? If we were going to Enceladus and flying through the plumes and we took samples, right? What would it? I mean, that might be a weird question because there's a point where you actually have living critters. That's clearly conclusive, right?
Yeah.
But non-living.
Well, let me. So what I'm going to say is a bit half baked again. But check this out. Like if you look at Earth, you have all this oxygen gas in the atmosphere, and just like you alluded to earlier, oxygen is an element. As in O, the element O, like that's all over the place.
Right.
But it's that O2 gas. That's kind of an interesting fingerprint because it's like microbes did that.
Yes.
Right? And then there's there are all these different kinds of isotopes. And just as a reminder to those listening in, that's like when you have something like carbon, you got 3 different flavors of it, right? There's like a carbon 12 and a 13 and 14. And that has to do with the number of these things called neutrons, as we know, sort of stuck to it, right? So sometimes living things discriminate against one or the other, and they actually leave us what we're going to call it an isotope fingerprint. So when I look at methane on Earth, to give you a clear example, and I work with a very large mass spectrometer in my lab, for example, I can tell methane made by microbes versus methane made by volcanoes.
Oh, really? Because Mars is making methane. There's methane on Mars. Yeah.
But in order for us to tell if that methane came from, in order for us to get closer to figuring out if it's living things or dead stuff, we need to look at the isotopes. And that's hard to do.
You can't do that remotely. You got to need a sample.
So I'm not really sure if NASA has that tool. Maybe that's something you and I can look up after this. But I don't know that there are really high performance isotope analyzers like on Perseverance. I don't think that's the case.
Is it just by the mass? It just weighs more?
Yeah, it's a mass. Yeah, so you have to. That's what mass specs are good at. Yeah. And so that's the brilliance of sample return. Like we got to get samples back from Mars. Yeah. I would love to see us do this internationally and really put all of humanity's ingenuity to looking into what is the evidence in this rock, right? But we have to bring them home. I don't think we can do it on Perseverance. Yeah.
If there was life on Mars, what does that tell us about Mars?
I think broadly speaking, it tells us that there may have been a time in the past where Mars had maybe been in a position where we had liquid water, and it's looking like there probably was liquid water on Mars. And if that's the case, and I don't know enough about the core of Mars, but if there's any heat coming out from Mars in the past or now, if you have that temperature gradient, which you mentioned, that's cool, Hakeem. Because now if you got liquid water and you got some heat, it's not like the elemental composition of Mars is that different than Earth. I mean, it's not exactly the same, but I wouldn't be surprised. I wouldn't be surprised if we found microbes. I just wouldn't be.
It seems like we keep getting teased with these, there was the Martian meteorite with the microbes in it. There's the methane on Mars. There's water. Look at, there's still, remember the crater where you can see the seasonal changes. Then there's the water under the polar ice. All these little teasers.
Yeah, they're teasers.
Yeah, when are we going to get I want a catfish from Mars. Like, when are we going to get to the real life?
You might be waiting a while.
Real smoking gun.
So it's going to be a while for that catfish, Hakeem. But I'll say, look, I think that here's a question for frankly all of us, all of humankind. We a lot of us want to know this answer, right? A lot of people do. And if we do, we should be asking ourselves, what is a better way to get more conclusive evidence? And so I'm a big fan of this sample return idea. Because so many of the tools we have on Earth, we can't put on spacecraft cheaply or easily or practically, right? But if we can get a sample back, that changes things. And again, this just is something that I think is in the heritage of all of humankind. We should look at this together and figure it out. To me, if we get, and if I could wave a magic wand, what I would love to do, you're talking about probes, I'd send out probes to 6 best candidate places on Mars, or maybe 10. Just grab a sample. I want to look at them. And then I'm not going to promise everyone we're going to find life or not, but I'll bet you if we came back with 6 or 10 samples, we would have a much better idea if there was life, and we'd have a much better idea if there wasn't, we can walk away from it.
How about this? Instead of sending rovers, what about we send a team of geologists to 6 sites on Mars?
3
geologists.
That's it. That's a. So I think this is a cool idea. I also, part of me is like, can we do this with robots? This question came up during Apollo, right? Like, do we send people or do we send robots? Right? Because at the time when they were thinking about sending humans to the moon, this debate was raging. But I think, Hakeem, people were like, sending people to the moon is more than just grabbing rocks, isn't it? And so sending people to Mars, I get it, right? So if you really just want some samples, send some robots. But you're talking about something that I think is bigger, and it's an important question.
Well, I want to hear what you think about this question, because whenever I have a conversation like this and it's public, and there's a ability to comment on the conversation, someone always invariably points out, oh, you're talking about doing this research using these rockets. This costs a lot of money. There's a village where they don't have clean water. Why are you doing this? Isn't this a waste of money? I have my answer for that type of question. Part of it has to do with understanding how economies work, and that it's not a fixed amount of money and it's here or there. But how do you address that particular criticism that we as scientists are often confronted with?
Yeah, and I think you and I have what you just said tracks and resonates with me. I would put it this way. I would say that sometimes we act like we've got this kind of zero-sum game, if you know what I mean by that. You have $100 and that's all you got. It is equally important that we solve the problems of clean water around the world. And it's equally important we solve problems with clean water in the U.S. Let's go back to Flint, Michigan, for crying out loud, right? These are real problems. Not going to space and not doing the science isn't going to solve that problem. What I really want is, again, if I could wave a magic wand, I want all people to recognize that, working together, like we are greater than the sum of our parts. These are all addressable problems. That's the bottom line.
These are all addressable problems.
Right. Yeah, and there's a lot to be said for the fact that technologies that get developed for studying the world around us often end up helping people. Like, this is not uncommon.
And they create new money.
They create new money. It creates value, creates jobs. Yeah. So we can do better than we're doing.
Yeah. It's not harnessing money, it's creating money. It's the opposite.
That's right. It's not, there isn't just one pie. We need to be baking more pies and thinking about who needs help and where and how do we get there, right?
Understood. Yeah. So I feel, Mars might be overrated. And the problem with Europa is that it's within Jupiter's radiation belt.
Yeah.
Right. But Titan is different. And I don't, it's within Saturn's protective magnetic field, but outside of its radiation belt. So do you have any ideas of what life might be like on Titan? Because you're into methane. It has these hydrocarbon lakes and this atmosphere that's Earth-like in some ways.
Well, I'll start by saying, Hakeem, this is why I love working with you and astrophysicists and cosmologists, because if I don't listen to you and listen to my colleagues who think about magnetic fields or think about gravitational pull on planets, like I'm missing something. I go in there with all my own narrow assumptions. So when I think about Titan, putting my biology hat on, I was like, great, okay, there's, methane, that's a good start. But I start thinking about, all right, so there are microbes on Earth that can use methane and oxygen and harness energy.
Yeah.
Or they can use methane and sulfate or whatever. I mean, there's a whole bunch of combinations.
Yeah.
I don't know what's possible on Titan. So I'm super excited about Dragonfly because I think it's going to give us
the space mission. Dragonfly is going to fly around the surface. Will it have a boat too?
I think I don't know that it'll have a boat. I think it's intended though to land on these sort of skids, right? And kind of be able to look at these bodies of water. I think I have to go back and
Bodies of liquid.
I'm sorry, did I say water?
You said,
I meant to say liquid.
I know
in fact, I was thinking about that every time I hear someone talk about Titan and they talk about oceans. I'm like, try to remind people that this is like liquid methane or something else, right? There's a lot going on.
Right.
Could life live there? I don't know. But
it's a very organic world.
Excited for Dragonfly.
Yeah. I don't know when it flies. I went to the APL, the Advanced Physics Laboratory at Johns Hopkins.
Yeah.
And they actually have a vending machine of mission T-shirts.
Isn't that cool?
So I got a Dragonfly T-shirt.
I love it. You and I did the same thing. I just gave a talk there like 4 months ago. I'm like, this vending machine rocks. Yeah,
right, exactly.
Just pumping money in.
So what do you think about panspermia? You say that these, if you're on the surface of an asteroid or something like that, okay, it might be tough to survive the radiation environment. But then there are microbes that are more radiation hardy, and you could also be inside that asteroid living on uranium or something.
You nailed
it.
You totally nailed it.
You
nailed it. Yeah. So we know that we study microbes that live inside rocks today. We call them endolithic. And I want to make it clear that microbes aren't going to live in something that's like a glass bubble, because there's no exchange with the environment. So they'd run out of food, right? And then they can't do anything.
Yeah.
But there are big chunks of rock, carbonates, sulfides, all sorts of other kinds of rocks where you could have a microbe, centimeters or meters inside this rock, and there's enough exchange with the outside world that they're doing fine. Now, you tell me, Hakeem, if a rock like that can shield them from, I don't know, ionizing radiation or whatever. Now we have an opportunity. To see how microbes might move between these bodies. I don't know. I just think it's a little arrogant to just rule it out, or arrogant to assert that it had to have happened. That's why we do the work, man. That's why we do the work.
But man, when you look at like Earth, I think about the moon.
Yeah.
I'm like, okay, Earth is the moon is only 1% the mass of the Earth.
Yeah.
Right? A quarter the size.
Yeah.
So it's a smaller target and it doesn't have as strong of a pull. But it's covered in craters.
Right.
And some of them are massive.
Right.
Imagine how beat up the Earth must be. How much stuff must have just slammed into Earth. Now, I'm not saying that they brought microbes, but what they may have done is kick parts of Earth out into space, these giant chunks. And we know Earth had microbes at certain times, right? I don't know if, it's most of those impacts happened right as life was getting started, so, who knows?
That's cool, Hakeem. I like the way you describe that, because what you're saying is maybe a rough way of putting this, and correct me if I'm wrong, but there was a time in Earth's history, let's call it about 4 billion years ago, where there were enough kind of asteroids floating around, knocking the bejesus out of these planets and bodies, that there could just have been a lot of exchange. That's what you're saying.
That's what I'm saying. Yeah.
That's cool.
Yeah. And that's within our solar system. And now we've come to the time now where we're discovering objects from other parts outside our solar system entering our solar system. And certainly there would have been collisions there.
Right,
so,
100%.
Yeah. And these microbes are so hardy. I remember seeing a study recently of some little pocket of microbes that were found to be still alive after being inside their rocks for millions of years. Is that a common thing in your field?
It's a common thing. It's such a common thing. And again, they share the same basic building blocks of life that we do. But remember, I was talking about this sort of deal with the devil that animals made.
Right.
Like, we get to be all complicated and smart and big and all those things, but we don't actually tolerate a lot. At the end of the day.
Right.
But these single cell microbes, right, they can put up with a lot. That's why we have them growing on the walls of nuclear reactors, or why they live, in the bowels of a ship or on spacecraft.
They grow on the walls of nuclear. I never heard that before.
Pipes, I should be more clear.
Pipes,
but they grow in there. So
but they're in a high radiation environment.
Yeah, absolutely. Doesn't phase them at all. And in fact, like, the Department of Energy has invested money in saying, can we use these to clean up uranium messes that we've left, right? Because you can grow them and they can go down there and turn them from one kind of uranium mineral into another that's less water soluble. It's a good way to keep it from getting into water.
Wow.
Yeah, so they're awesome, man.
Hey, everyone. If you're loving this podcast, please go ahead and like us or leave a comment. And also make sure to subscribe so you never miss an episode. Your support means everything and helps us reach more curious minds like yours. Now back to the show. All right, so let's play a little game.
Yeah, let's do it.
It's called Two Truths and a Lie.
Yep.
And I'm going to give you 3 headlines, and you tell me which one is a lie. All right? First one. Slime mold composes music, furthering evidence of intelligence. And I'm assuming this headline is talking about slime mold intelligence.
Yep.
Second one. When you move house,
your
microbial aura moves too.
Yeah.
And the third one, plastic-eating bacteria turn waste into useful starting materials for other products.
Slime mold's a lie. The other 2 are true. That's my guess.
You nailed it.
Yeah, that's my guess.
So here it is loosely based on a real headline that they use electrical signals generated by slime mold to create music.
That was cool because I
you already saw it.
I think I saw it because I was like, I know. I'm sorry. It's kind of a cheat, right?
Well
It's kind of a cheat.
Too well read.
But that's so cool because someone was like looking at electrical signals, not just in slime molds but in plants, and you can translate that into a sound, and it's kind of neat.
Yeah,
I'm going to
that's done in astronomy as well too. It's called sonification.
Wait, really?
Oh yeah. So a lot of stars pulsate. Right? And so it creates this frequency, right? This waveform with a particular frequency. And it's not just an up and down, it's like, right?
That's cool.
Yeah.
That's cool.
And the thing about that is because when we get those plots, normally you see it as a plot.
Yeah, sure.
And you want some software to classify it as this type of star, that kind of star.
Yeah.
The software isn't as good, but the ear is such a great classifier that you let groups of students listen to them. They're like, okay, it's that kind of star. Delta Scuti, SX Phoenicius, RR Lyrae.
Okay, that's pretty badass. I did not know. That's so cool. So we need to get this in the hands of some jazz and hip hop artists. Kind of like, so we're like, hey,
hip hop artists take all kind of sounds. I remember when Timbaland made that Aaliyah song that had the baby, and everybody was like, "Wow, it's so cool!"
Exactly. That's cool, Hakeem. Thanks for sharing. Yeah.
All right, so let's go back to you and you.
Sure.
You and you.
Sure.
Because you have an interesting personal story. Okay. We touched on a little about this chatting in the green room. Right. You mentioned to me like, you know about my history in LA. Yeah. Growing up with my cousins being members of the Crips gang and robbing banks and all this kind of jazz. Right. You're from similar neighborhoods. You went through. So let's talk about number one.
Yeah.
There's this thing that happened to me when I left Mississippi and showed up at Stanford University, no one could understand me when I spoke. Right? And I had to change the way I speak.
Yeah.
And so I learned later that there's this phrase called code switching.
Right.
And I remember at one point, my mother visited my house some years ago, and I had a VHS tape of a talk that I had given at NASA. She watched it, and I'm thinking, oh, Mom's going to be so proud of me. And she goes, who the hell was that guy? I know you. I don't know who the hell that was.
That's
right?
funny.
Right?
Yeah.
So you grew up as a child of immigrants, and you lived in your neighborhood. You became science interested. Let's go into your background a little bit and tell me about your path to becoming interested in science, your social dynamic that you lived through.
So as a kid, and my parents being immigrants from Egypt, there were a lot of things that I wanted to do as a kid that other kids were doing. Certain clothes I wanted to wear, or certain movies I wanted to go see. And my parents were like, no, that's not what you do, right? And there were times where I would even be with my folks at some parent-teacher meeting, and they're talking kind of past each other because they're coming from two different cultural references. For my folks, teachers are held in reverence, and in Egypt, you go and you do what your teacher says, you bring them gifts, you do all this. There's things that you just don't do here.
Right.
And this sucked as a kid because I'm trying to teach my parents and be a kid and learn from my parents. Man, it was hard.
Yeah.
And so I think an interesting thing happens to the children of immigrants or different communities as you go from one to the other. You learn how to translate. And what I mean is, growing up, I realized that for my parents, the science that I did made sense, made most sense if I presented to them in a certain light. For example, when I said I want to be a marine biologist, they were like, you're talking like Shamu? But if I said to them, I want to be a professor, for them culturally, that was relatable because teachers are held in high regard. And so I learned that different people understand the world through their own lens. Hakeem, you know this as well as I do. And so learning how to listen to different people from different perspectives became a skill.
Yeah.
And today I think it matters because as I talk to other scientists, or here's a good one, as I talk to policymakers, I've done some work with the United Nations on treaties for the ocean, I understand and I'm aware that people are speaking from a different vantage point. And that helps you hear what it is they're trying to say.
Yeah.
That's been a big part of my professional life, is learning to listen.
It's clear from our discussion that you care deeply about humans and you love this science that you're doing. And so how do they combine, right? So we have the future of humanity and microbes, just as they have been a part of our past, beer, yeast, right?
Right.
How are they going to shape that future?
Yeah, I think we're at this point where humankind is beginning to understand and appreciate the role that microbes have played in shaping this earth and us, right? It's only been the last 10 or 15 years where we've been talking about the human gut microbiome. And that was a game changer in that it got people thinking about microbes doing good things for us. So many people think about microbes from that point of view of pathogens, right? The 1,000 or so microbes that cause human disease. And now they're beginning to realize, oh, my well-being is enhanced by these microbes.
Yeah, who doesn't love bread and butter?
Exactly. And it goes beyond that because microbes are the world's best chemical engineers, right?
Wow.
They really are. And so we have this opportunity now as humans to start asking, how do we work with microbes, to cooperate, if you will, with microbes, to get them to solve some of our problems in terms of cleaning up pollution or even producing new materials and new pharmaceuticals. Let's not forget that microbes play a huge role in the development of new drugs.
Oh, really?
Absolutely, because we can ask microbes to make certain chemicals and we can test those to see how they affect human cell lines. So you can see, is it a toxic compound or does it do the thing it's supposed to do? They are used all over the place.
I just thought of it. Penicillin.
Right.
Yeah.
Absolutely.
Game changer.
Total game changer.
Yeah.
And so that is one classic example of how microbes have really come into their fore because we're beginning to really understand just how much good they do for the earth and for us.
Wow. What about energy generation? That's a big topic in the future of humanity. Are we using microbes to generate come up with new energy sources? Is that a thing?
Yeah, I think, there's so many different ways microbes touch on that. In my world, I do a lot of work on these devices called microbial fuel cells. We can harness electrical power from microbes, not a bunch, but enough to do interesting work in the bottom of the ocean or the middle of Kansas.
Wait a minute. So you basically make a
call it a widget.
Bug battery.
Yeah, that's it. It's a bug battery. Yeah. And there's a bunch of research that's gone into this, and scientists are like, can we generate enough power to power cities and the like? And all this work is still going. But as for right now, we can generate enough power to do interesting things with sensors. But that's the tip of the iceberg. Let's talk about all these rare earth elements that are a hot topic now for batteries.
Right.
Microbes are really good candidates for recycling those rare earth elements. And more research is happening now.
Define recycling.
So, let me explain. So when we build a widget like a laptop, at the end of its life, which sadly, is too soon because we're such a consumer society, that circuit board gets smashed up. And you can use industrial processes to heat it and get some stuff off. But those rare earth elements, just by their nature, are sticky. And I don't mean literally. I mean, they mix, and it's hard to separate, say, the element tellurium from the element gallium. Or something like that. I use those two as examples, right? But it's hard to disassemble them. And so chemically, it's so expensive to do that. That's why we don't recycle those electronics that much. But microbes are very good at specificity. You could, if I think with enough work, we can find a microbe or even engineer one that we can feed it a bunch of broken computer chips, and it's going to pull off the tellurium elements and put it over here.
Oh, wow.
How cool is that?
That is super cool.
That's what microbes are good at. They're the world's best chemical engineers, period.
I love that. Dr. Peter Girguis, this was amazing, sir.
Pleasure's mine, my friend.
Man.
Yeah, that was great. Thanks for all you taught me, too. This was fun.
Bruh. I think the teaching was going in this direction. And I really appreciate it, man. That was awesome. I can't wait for our next conversation.
Pleasure's mine. You know where to find me. I look forward to it.
All right.
Thank you, sir.
Thank you, sir.
Be well.